Well, we have algebraic expressions and sets of numbers today. So a variable is a letter used to represent any number. Usually the variable is either a x, a y, or a z. For some reason we generally use those letters to be that, but it could be any that you wanted. A constant is either a fixed number or a letter that represents a fixed number. Now most commonly in terms of constant terms, it's 5 or it's 3/4 or it's 0.2 or whatever the number happens to be. But also we'll see things like a, x, and a might stand for a constant term, meaning it stands for a number, and the x is standing for a variable. So an algebraic expression is formed by a combination of numbers and variables connected with operations, the operations of addition, subtraction, multiplication, division, also raising the powers and taking root. Algebraic expressions are noted by the absence of an equal sign. Now, for example, 3x plus 5 is a combination of the constants 3 and 5 and the variable x. 5a squared minus 6a plus 40 is a combination of the constants 5, 6, 40, and an a and an a being the variable. Now notice that it is also taken to a power. We have a subtraction, we have an addition, and in between here, of course, we have multiplication. And we could also have a division, something like y to the 4th minus y squared plus 15 divided by 4y. So all of those are examples of algebraic expressions. Now, when we evaluate an algebraic expression, and a lot of times on tests, we will just get the word evaluate with numerical value for each variable into the expression and simplifying the results. Now, for example, we might have an algebraic expression like 5x minus 2, and we will be asked to evaluate it for a value of x is equal to 8. Well, what we do is we take that 8, and in that expression, we replace that x with the 8. If we don't have a sign between a letter and a number in an algebraic expression, that indicates multiply. So in this case, what it means is we're going to multiply 5 times 8, subtract 2. So we'd get 40 minus 2, or 38. Now if we have 3a squared plus 2a plus 4, and we evaluate a for minus 4, it means we're going to replace the a everywhere with a negative 4. Notice that we'll be raising a negative 4 to the second power, so we probably need to enclose that in parentheses. And when we do so, then we square that negative 4, we get a positive 16. And of course, over here we have 2 times the negative 4, so we get a negative 8th value there. Combining, then, we would have 3 times 16. So that would give us 48 minus 8, which gives us 40, and add 4 to it, we get 44. Now, sets of numbers. The first set of numbers that were ever born were probably natural numbers. They were used for counting. So they begin with a 1, a 2, a 3, a 4, a 5, a 6. And they went forever and ever, as large as you wanted to be. Now notice out here at the end we have these 3 dots. That's called an ellipsis. And that indicates that these numbers go forever and ever. So the natural numbers are really an infinite set, means that they could go forever and ever, and we can't count them all. Or if you could count the last one, you could always add 1 to it and get the next one. So the natural numbers start with 1 and go forever and ever. The whole numbers, on the other hand, start with 0. So the only difference between a whole number and a natural number is that 0 has been added into the mix. They both are examples of infinite sets. Now we came along with the integers. The integers start from a 0, which is our origin, our starting point, and down to the left we go in a negative direction. Notice that we have the ellipsis that indicates it goes forever and ever in that direction. Up on the other end, in the positive direction, it goes forever and ever. Notice that there's no positive signs on 1, 2, and 3. But if we don't have a sign, we assume it to be positive. 0 is the only integer that is neither a positive nor a negative. Now, the rational numbers is the set of all numbers that can be expressed as a quotient of integers with a denominator not equal to 0. So, if we can take one of these integers and place it over a non-zero denominator, we make a fraction out of it, and that's what really our rational numbers are. All of those numbers that we can't do that with are called irrational numbers, and numbers like pi or non-repeating, non-terminating decimals are irrational numbers. And if we combine both these rationals and these irrationals, then we form the set of what we call the real numbers. Those are all the rationals and all the irrationals combined. So a number line is simply a line so that each point is associated with a number. Now we have an infinite number of points along that. So we'd have the negative numbers down below 0, the positive numbers up above 0, numbers in between like negative 4.8 and 1.5 would be in those positions as shown. Now our vocabulary words then that we come out of this section with are variable, and that's a symbol used to represent a number. An algebraic expression, which is a collection of numbers, variables, operations, grouping symbols. There are no equals, or neither are there inequalities, less than or equal to. In describing some of the previous set, we use a symbol called the ellipsis, and it means to continue in the same pattern. The members of a set are called elements, and if we list them all, then we said we form a roster if we have an attempt at listing them all. A set can also be written in what's called set builder notation. This is a notation which describes the members of the set, but it does not list them. Now here would be an example. It would be that we would use the set symbols on each end, and we would say it is the set of x's, and remember now x is like a variable, so it's going to stand for something. So the set of x's, and then we kind of put a pipe symbol in there, and that symbol right there is read such that, and then we have x is an even natural number less than 10. So we have described for you, without listing them all, what numbers we mean. So the set of x's such that